Hello everyone and welcome back. Now we're at group problem part 2. Return of the problem. So you have your calculator, you have your friend nearby, you solved that first problem and now you're ready to move into the second. Now what are we looking at? Well, we have some sort of spring right here and we're pulling it back. And as we compress it, energy is stored in that spring. Then we release that. It puts energy into the ball gains kinetic energy, and it goes up the track. What we're trying to figure out is what is the normal reaction of the ball, or the track on the ball, when theta is equal to 60 degrees. And what is the speed at that point? So I'm going to let you try this out. And how are you going to do it? Well, conservation of energy and also choosing the right coordinate system. Conservation of energy and choosing the right coordinate system. Those are going to be the things that are going to help you solve this problem. So without any further ado, I will give you the countdown. 3, 2, 1. Now you've paused your video, you went and tried it, you rocked it, and you came back just because you like to hang out with me. Or it didn't go so well and you're back because you want to see the answer. Either way, you're back. So let's watch it. Now to solve this, we probably want to set our datum at point A. It makes sense. We say we have no gravitational potential energy at first, just our spring energy, and then that gets translated into gravitational potential energy and kinetic energy as we go along. Now, we set our datum at the bottom because we want to remind ourselves that energy is being stored as potential energy as we go up. So less and less energy will be available to be kinetic energy as we go further and further up. More and more of it's going to be stored by gravity. So if we then set up our equations, we know we have no kinetic energy to begin with. It's all just spring energy. And afterwards, we're going to have some combination of kinetic energy and gravitational potential energy, which we can figure out. We know how much potential energy we'll have. It's going to require a little bit of work here, but if we look at this, we can figure out the height difference by determining this component right here. That's not too terrible, it's just not very fun. So we have this component, which I'm just going to call D, and we'll say that this one right here is the total distance. And so D minus D is how far I've been moved. And that's where this is coming from right here. That's the total distance. This is the component. I subtract the two to get how high I have actually moved. Now if I solve this, what I get is that my velocity at point B is 5.94 meters per second. And that's going to be tangent to that surface. I want to find the normal force, and my velocity is tangent to the path. If only there was a coordinate system that would help me with that. But there is. I'll be using my normal tangential coordinate system. So in this case, there's only two components. I have a weight pulling down, and I have a normal force, which is going to be perpendicular to my path. And if I then solve for that, I can solve for that normal force. So if I set up my equations properly, I'll get that sum of the forces in the normal direction will be equal to my mass times my acceleration in the normal direction. I've got two components in that direction, which are the normal force and my weight. Luckily, I know my weight, I know my velocity, and so that normal force is causing an acceleration of, right here, 5.94 squared over 1.5. And so I can then solve for my normal force. Now remember, even though we say there's an acceleration in the normal direction, that is just turning my ball. It is not pushing it off, making it fly into space. Okay, so remember that. It is just turning my ball. It is not actually pushing it off. So that's it. We have solved this problem. We wanted the normal force, we got it. We wanted the velocity, we got it. And getting that velocity was just so simple thanks to our conservation of energy equations. But like I said before, and I'll say it again, this class is cumulative. You're going to have to keep on using your earlier material as we move further and further along. So thank you for listening. Thank you for working so hard, and I'll see you all next time. Bye-bye.